out there. And we are confident we'll be able to complete it at least before 1:45. So I'll request Alina to start the proceedings with the first presentation by P&F.
We would like to call upon our next speaker, Mr. Arasu Thanigai, Technical Head, Pepperl and Fuchs, to give a presentation on innovative technologies. So we would request you to come on the stage.
Good morning. Can everybody hear me? Okay, so first of all, I would like to thank you very much for ARC and also to Pepperl and Fuchs to bring me on the stage to share some of the ideas. Okay, that's not a good start. Let me put it to... So today my topic is going to discuss about some innovations in the technologies, and particularly when we talk about oil and gas industries and how we did the instrumentation in the past and what limitations we faced and how are we going to solve these problems. And that is basically my information. And further to this, and we also have a lot of additional information in the field. So when we move from conventional into the digital technology, like Fieldbus and different types of field buses in the market, and there are a lot of informations available in the field. And also initially we faced problem with how do we properly utilize this information and how do we commission the digital plants in an effective way. And what are the methods we can adopt to bring or to simplify the commissioning process. And that is going to be the second part of my presentation. So first, since today's concentration, I mean, we are going to focus on the oil and gas industries or chemical industries. And of course, first we need to get to the point that what is really the hazardous area means. So why do we need to use our technologies into some special applications, like where we have to have some considerations? How do we limit the energy, and how do we prevent certain kind of accidents that used to happen in the past, or even continue to happen if we don't do things in a proper way? So let me give some examples why we are taking this hazardous area classification into very serious considerations. So in the past, in the early 19th century, and also in the recent years as well, and there's been some unexpected events happen. So this is one of the example what happens in one of the chemical industries in BASF in the early times. And due to some reason, some of the electrical equipments and release some spark, and that caused a big explosion near the Frankfurt in the Ludwigshafen plant that killed almost like more than 500 people and destroyed complete village, the surroundings about that. And the main reason is the hazardous area classification consideration was not done properly. And then of course, some of the sparks, electrical sparks, lead into this explosion. And similar thing happened in quite recently as well. And in this century, and as well in Algeria, this is one of the petrochemical industry, and that was completely destroyed in this explosion. Again, the reason was some of the electrical spark, and the spark which might be electrical or some other means that created this ignition. And of course, we have some means to minimize or eliminate such kind of unwanted situations. And another example, in so-called developed countries like US, also witnessed some kind of problems in quite recent years. This has happened in one of the BP facility. It costs almost like $2 billion US. It also brings some loss to the human life as well. So all these things happen mainly because we have an unavoidable situation in most of our chemical industries in a petrochemical atmosphere. So we have the combustible substance that cannot be avoided. So for some reasons, of course, it is always present around this processing locations. And this material itself cannot create the explosion. So we need some other components to make it ignitable. So the other components, what we need is the oxygen. And of course, it is present everywhere, that cannot be avoided. And these two components is almost impossible to avoid in the situation, in the practical applications. And these two components itself could not create the explosion. So we need another one to ignite these two substances. So we need to have some ignition source. This ignition source can be in any form. It can be in the form of electrical, it can also be in the form of mechanical, it can come from some atmospheric behaviors like lightning or radiation, whatever it is. So there are different factors which will contribute to the source of ignition. And this is the only thing what we can minimize or try to avoid. So especially when we talk about ignition source, most of the time we mean is the electrical source of ignition. So when we bring the energy into the field to power some devices, and especially in the chemical industries, oil and gas, and where the area is classified as a hazardous area, and then we have to limit the energy. And this method, of course, works very well for certain kind of methods, what we call as a conventional method. And we have a DCS IO card, and then we have one transmitter, and that's going to power a single device. And even we limit the energy in the control room, the energy that is going to be applied in the hazardous area is more than sufficient to drive a single device. But this brings a problem when we move into digital applications. So when we bring the complete plant, when we are moving from conventional to digital, we are not going to connect one single device to the DCS. A single cable can have more than 12 devices. In some bus systems, it can even be up to 20 or even more devices. So the moment we limit the energy at the control room, it's going to bring us a problem, practical application problems. And this was the case until recently. And there are different ways how we can overcome the situation, but that also has some limitations. And this led into different area of classification, so we don't spend too much time on this. And since we are in the oil and gas application location, we know how the locations are classified. And basically, we follow either European-based or the American-based, North American-based. We call them zones or Class 1, Division 1s. And a typical example of a storage tank, and we would classify them in different areas like Zone 0, Zone 1, and Zone 2, depending on what is the intensity level of this combustible substance. So if it is going to be very intense, for example, just above this tank, and of course, that is going to present almost as long as there is a liquid, and we are going to call this a Zone 0. And when the pressure increases, we have to have some system to release the pressure. So the vent, whenever it opens, the concentration of this particular substance is also going to get somewhat intense at this location, and that's going to be Zone 1. And further to this, and this combustible substance, if it is going to be a gas or whatever material, that is also going to creep around the storage locations. And to some extent, we also call them Zone 2. So we also have the equipments classified to be placed in similar locations. That has to be certified, and it has to have some limited energy applications. So this is a typical way how we do that in a chemical or oil and gas industries. So there are different ways how we can limit the energy that is going inside the hazardous area. Some method is called flame-proof. So if it is going to be a high-power device, the only way we can limit is we let the energy go all the way to the hazardous areas. And of course, we limit the complete atmosphere. Even if something happens, let's say, for example, some explosion or spark or whatever it is, we are not going to let it come out of the enclosure. And that's the way we do this in flame-proof. And we have some other methods. And one of the most, or the least expensive method, or the simple to realize, and is called intrinsically safe. So this is one of the easiest method, which is adoptable in almost every hazardous area location, not only in oil and gas, and different types of industries as well, and they adopt this method. But this is good enough, so almost perfect when we have conventional type of application. So we have one device, and that's going to be powered from a control room, so it brings the voltage and current in a limited fashion, and that's enough. But when we move into different type of industries, and when we go into Fieldbus level, there are different requirements. So that is totally different from conventional type of requirements. So here, we have to have at least 12 or even sometimes more devices on the single cable. And of course, we have to have an intrinsic safety. That means we need to limit the energy that is to connect all the way up to 12 devices. And the trunk cable distance or the cable distance in overall, a typical example in the Fieldbus or any digital buses, and the average requirement is about minimum 1 kilometer trunk cable, and overall it's about 1.9 kilometers. And also we prefer to have the less hardware at the plant. Being digital plant, we also try to minimize the number of hardwares. And of course, we also want to have some other features like redundancy at the control room, at the power supply and the DCS level, and etc. But applying the intrinsic safety in this location, in this situation, it's going to have some limitation. And if we limit the energy by using our traditional concept, the entity concept that is used in our conventional application, that's not going to work for digital applications. So that has got some severe voltage and current limitation, good enough to power one single device, not at all enough to have Fieldbus related applications. Then we moved into different type of intrinsic safety. We follow the similar concept, but we think about in the digital way of doing this intrinsic safety. So the PTB authority, together with few other companies, PNF is one of them, and then we come out with a new concept that is going to be applied only in Fieldbus application. Still follows this intrinsic safety, but only in Fieldbus application. So we made some improvements and then come out with Fieldbus intrinsic safe concept. And that was introduced early 1990s, and then still has some limitation. It's better than the conventional type of intrinsic safety, but of course it has still got some limitation. I mean, we still need to limit the energy, the voltage and the current, and not sufficient to have all the criteria what we just saw. Then we moved into different type of intrinsic safe, what we call as a high power trunk. This is one of the most adopted method at the moment to have the intrinsic safety. And of course, it overcomes all the limitations, whether by entity or FISCO way of doing the Fieldbus intrinsic safe or hazardous area application. And of course, though it meets almost every requirement, it still has some limitations. The trunk and the spur have to follow certain different standards. The spur lines, that is from the field junction box to the device, can be intrinsically safe, but from the control room all the way to the field junction box, we still need to bring the higher energy, so that cannot be intrinsically safe. So how we do that is, actually, this is the first method in the 1980s, in the mid of 1980s, when the Fieldbus was introduced, when we tried to adopt the conventional intrinsic safety into Fieldbus, and this is how it looked like. We have a power supply that limits the voltage and current according to the conventional intrinsically safe. When we put more devices, this current is not sufficient to connect anything more than 2 or at the max 3 devices. Or the voltage is not sufficient to drive not more than 200 meters at the worst case. And if you consider all the safety factors, it becomes even worse. And the biggest problem is this intrinsic safety by principle does not allow redundancy. So we cannot put one more power supply in parallel. That is totally forbidden. If you put 2 power supplies in series, the IS parameters is totally not compatible. Then we move to FISCO, Fieldbus intrinsic safe concept. We improve the voltage to some extent, not to the great extent, but of course we also classify the application regarding gas groups, 2C and 2B, and then we put a different current characteristics. But even though the current is sufficient to drive certain number of devices, the voltage is the biggest problem. And again, the traditional limitation of the intrinsic safety, the redundancy, it is absolutely not possible. So though it gives a certain improvement, but again, it is not practically used in almost every plant, and because of some practical limitations. Then what we did, we moved into a different type of intrinsically safe. And this is one of the method what we call as a high power trunk, officially recognized by the Foundation Fieldbus and other types of Fieldbus like Profibus. And what we do not do the intrinsic safety in the power supply. That is the biggest problem if we limit the voltage and the current. So instead, what we do, we allow up to higher voltage and higher current, and we bring the energy to the junction box, and we have some barriers, safety barriers inside, and then this does the limitation. By doing so, we eliminate all the limitations like voltage, the higher power, the redundancy, building the diagnostic on board, and as well as other practical problems, all eliminated. So this meets almost the entire requirement of the intrinsic safety hazardous area application. But one of the main limitation here is the trunk line, what we bring from control room all the way to the field, it's not intrinsically safe. So compared to the previous method, the intrinsic safety starts from the control room. So the trunk and as well as the spur cable, everything is intrinsically safe. But it has got so many limitations. But the second method, though it provides all the advantages, we still have certain limitations, especially the trunk cable, which goes from control room all the way to the field. And if somebody, we have certain checks and marks, and it has to follow certain guidelines and standards. But unfortunately, if the technician is not trained enough, or is somebody going to pull the cable, the trunk cable, and that's not going to give some good results. And to eliminate this, so now we recognize the situation. Though it is acceptable in most of the industrial applications, and we want to make sure the safety is achieved throughout the plant without compromising the highest power. So how do we do that? So it has to be intrinsically safe, but it also has to give the higher power. And what we did is we rethink about how do we do the intrinsically safe. So the main problem is we have to limit the voltage and current, and that is the traditional way of thinking the intrinsic safety. So now we move one step ahead, and we thinking in the other direction. So this is a different gas group, what we normally encounter in the oil and gas, petrochemical industries. And what we do, we limit the energy. As long as we follow certain gas group, we limit the energy that is below the gas group curve. So this energy is not able to limit as long as it stays below the curve. So when we select a power supply voltage, for example, NTT or Fisco, always lies in this region. But this is not good enough for a Fieldbus or digital applications. So now what we do is we move to the other side. And this is what we are doing in the new type of intrinsically safe. So we thinking from the other side, the higher power side, and how do we do the safety circuit? And how do we make sure the intrinsic safety is achieved? And this method is called the dynamic arc recognition and termination. This is one of the innovative method and that has been introduced in almost 3 years back. And it has won different various industrial awards and around the world. And so here what we do, so instead of limiting the speed, for example, if you drive in analogy, when we compare, you can drive the car, with a certain low speed, for example, 2 kilometers or 3 kilometers per hour, and of course it's going to save. And even if you meet any accident, that's not going to create a damage. But instead, if you put a perfect and reliable brake that stops the vehicle no matter what speed it travels, and that's going to bring a lot of advantage. So we are not going to drive the car with the dead slow, but we are going to have it with all the advantages and also the safety. So that's exactly what we are doing in this dynamic arc recognition and termination. So just for an example, when we take this circuit, so we take a power supply, unlimited, we put a cable, and then we connect a load. So what happens if there's somebody break the cable? So in the plant, maybe somebody pulled the cable, and the energy is unlimited here. So once the cable is broken, and the current is going to drop. Of course, the current will not flow, the current will go back to the source. And at the same time, because it is an inductive circuit, the cable is nothing but a combination of inductance, and it's going to build up a voltage until to a certain level, and after that it's going to go back to zero. And this is how the electrical characteristic, when you cut the cable, this is what it happens. The current will drop to zero, the voltage will build up, and after that it'll go back to zero. But during this time, the power is going to be constant because it's a product of voltage and the current, and even though it drops and one factor is increasing, one factor is decreasing, and the power is going to be constant, and as long as it is going to be constant for few millisecond region, and that is going to create the spark. So this millisecond region is good enough to create a spark in this cable. And for example, the critical phase is defined in the millisecond region. The microsecond region is in initial phase, that's where the dropping and the increasing takes place. And this is what happens in the normal unlimited energy circuit. And in intrinsically safe, what we do, we limit the voltage, we limit the current to a so low value, we also limit the voltage to a so value, the power is kept to extremely small level, and even though it breaks, the cable breaks, it's not going to create the problem. But in the dynamic way, what we do, so as long as we do not do the limitation, in the intrinsic safe, the normal intrinsic safe, whether we have a fault, no fault, the power supply is always going to limit the power. And in the dynamic way, we are going to leave the power untouched. And when we see any problem in the field, as long as any cable break or anything short circuit or anything happens in the field, and that is going to be detected in few microseconds. And the dot or this particular special circuit that is built inside this power source or whatever equipment, and that's going to detect this problem in the field or anywhere along the circuit, and it's going to limit the energy within less than 5 microseconds. So without compromising the voltage and the current. So in a way that we limit the energy only when there is a problem. And by doing so, and if you have a problem and if you have a cable break, your circuit is not going to work anyway. Functionally, it cannot work. The only thing what we have to ensure is the safety. And we are ensuring the safety by limiting this voltage and the current or the power level in less than 5 microseconds. And this is one of the demonstration equipment what we use, and this has been awarded with a lot of different types of awards recently. And just to give you some simple example, okay, so what we do here is there is a small circuit and which is about 40 volt and 1 ampere, unlimited energy. And when we make and break the contact, and you can clearly see that it creates a spark. And this is an unlimited source. And the same circuit, when we put the intrinsically safe, the same amount of voltage in the current, when we put in the special type of intrinsically safe, and when we have the similar type of equipment, and that is not going to create a spark at all. this has been demonstrated for a practical understanding purpose, but of course, the safety agencies, whether it is going to be BASIFA or PTB or all the safety agencies around the world, they already approve this technology. And the products available in the market to use this technology. And also in the recent Akima Fair, it has won the Innovation Award. That is the top prize, and every year almost, so this particular technology wins the award. And by using this technology, we can bring up to 50 watts, and still it can be intrinsically safe. And for a typical field bus, we don't need more than 8 watts. In a conventional, if you're using a traditional EXD equipment, where we have unlimited energy, whether it can be a high-powered DC, and it brings a lot of other restrictions. Your equipment is bulky, and then you need to have certain special maintenance procedure, gas permit, and so on. But in this case, and it can be 50 watt, your EXD devices, and once it is going to use this dynamic intrinsic safety, that can be a simple intrinsic safe device. We can do any maintenance online. So in field bus, the application is very simple. So we have a power supply that uses this intrinsically safe. The output is going to be completely intrinsically safe, and we limit the voltage and the current to a highest level that is sufficient to achieve any digital application. Achieves up to 16 devices, and each cable can be 120 meters, the overall cable, and the trunk itself can be 1 kilometer, the overall cable can be more than 1.9 kilometers, and so on. So it also brings a lot of additional advantages because it has been approved all around the world. It got the European certificate, it got the IECX certificate, and even the American certificate. So it has been accepted by all the safety agencies around the world. And it is also accepted by the different Fieldbus organizations. So if you go to any Fieldbus website, you will also see that the products which is designed according to this is also registered inside. So which means the Fieldbus, the digital application also realizes this is the way to move forward in order to bring the intrinsic safety with the highest power. And also it brings the enormous savings in the size of the, and as well as the practice how we do this intrinsic safety. The intrinsic safety can be done by this high power trunk, that means the unlimited trunk and the limited spur, and also the full intrinsically safe, and that also brings a lot of simplicity to the plant. So the main advantage or the benefits to the end user, which brings in terms of business perspective, is more economical at the control room, and as well as at the field in terms of cost, as well as in the size, and it achieves without compromising the requirement of the field bus. You can connect higher number of devices in the longest cable distances, and as well as it comes with the integrated diagnostic that continuously monitor the complete field bus architecture that reports all the information directly back to the DCS asset management system. And this is one example how we do that in the typical non-field bus or non-digital application. In a traditional way, and if you want to have any EXD-based equipment, and we have to have a different type of architecture, and different type of cable system, different installation procedure, different standards has to be followed. But the same equipment can be powered by intrinsically safe without compromising the power. It can be up to 50 watts. And by doing so, it avoids a lot of hardware and as well as the installation practice. It brings down the cost and as well as the simplicity to the installation. The second topic what we are going to talk about is we have a lot of information, especially when we have digital applications in the chemical, oil and gas or whatever industries. And when we are moving towards the field bus, we have a lot of logged information. So in the transmitters and also in the DC systems and also in terms of diagnostics, so what is happening into the system, and also to check your complete infrastructure, your grounding and shielding, your cable characteristic. And all these things has to be checked. This is part of the procedure, not only in field bus, but even in the conventional. So when we go for a site acceptance or factory acceptance, there are certain parameters have to be measured and documented. But when we are doing the similar thing, same thing in the field bus, and it used to be not so easy in the past, because there are different requirements during the FAT and SAT. So we have to monitor the complete infrastructure measurements and network validation, the noise characteristic, and we also need to check the cables, whether it has been properly installed, what type of noise or whatever external disturbance is coming to the cable, and so on. So in order to do that, we used to have a simple validation and check tools. Traditional devices what we use, a multimeter, some simple field bus testers, battery-operated oscilloscope to check the signal, and as well as a manual documentation procedure. So not only we have to measure the parameters in the control room, we also have to go and measure each and every field device, the parameter have to be measured, and the junction box, the parameters has to be measured. And now the diagnostic, since we are moving towards a complete digital, and the complete commissioning and as well as the troubleshooting procedure has been simplified by introducing the diagnostic at the advanced level of diagnostic, which is part of the complete power supply system. So this type of pluggable module that can sit on the power supply system that monitors not only the control room, that monitors the cable system, your grounding and shielding, and as well as every single Fieldbus device. And the complete infrastructure can be monitored. And not only it monitors, it exports whenever there's a problem happens, it gives the exact information to the DCS system. The technician knows if something goes wrong in the cable system, if the termination is not done properly, or if your Fieldbus cable running too close to a AC cable, for example. So all these issues, the technician will automatically know because this device will report if anything happens practically, and the DCS will automatically get to know that. So these are some of the examples how the system or how the diagnostic is integrated. The physical layer diagnostic is integrated into the DCS asset management system. So the integration is very simple. So every DCS is capable of doing this, or even an end user is capable of doing that. And we just put additional, so all the diagnostic devices would be interconnected, and then we put the common industrial Ethernet, which is one of the good practice that is used almost in every application. And the industrial Ethernet brings the information from this diagnostic all the way to the DCS asset management system. So regardless of whichever DCS is being used, the similar type of integration would be followed. And the DCS asset management system will indicate the number of devices connected and as well as the diagnostic information for that specific segment. So if anything happens, it raises alarm and it opens the software, tells exactly what happens, and then tell the technician how to solve the problem, where is the problem. And also it keeps the history, and even if the technician is not around, and is going to get all the information at the later stage. And different DCS system, it's exactly the similar type of integration. So moving forward with any DCS system, the integration is simplified, and we can get all the information, and all the traditional measuring devices is no longer required. Everything is automated, and even the report generation is done automatically. It generates a report practically in the PDF format or Excel format that simplifies the documentation. And also it follows a similar AG 181, that this recommendation from different foundation Fieldbus or a general Fieldbus standard. It compares whatever the parameter that is measured, and it checks with whether it is deviating within the standard. So if anything happens, it changes the color. The parameter will change the color. The same information will go to the DCS. What we see here, the screen, it's nothing but it's taken from the DCS platform. So exactly what we see here, that is what we see in the DCS application. And it adds a value to the complete Fieldbus infrastructure by monitoring the segment and diagnosing whatever problem happens, and it also advises the technician what is the problem and how do we eliminate the problem. And this is what we call the expert system that is built inside, that pinpoints exactly the problem, tells the problem and where is the problem and how do we solve. It also logs the date and the time, what type of problem happened. So it monitors almost every single information that happens in the Fieldbus. It also follows the international color code to indicate what is the status of the value, your physical parameter, external noise disturbance or whatever. And it also have built-in data logger. You can store the data for up to 2 years. Most of the diagnostic devices, and especially the physical layer monitoring devices, and this is one of the interesting feature. And this one, of course, we can also do this trending analysis, and if we want to, after 3 months or after 6 months, if you want to see the plant performance, your physical layer performance, you can download the data and then monitor the graph. And for example, you can see that what is the external disturbance coming into your plant, maybe the Fieldbus noise. So where does the noise come from? So what would be the source? So everything would be indicated in this software. And not only that, and measuring the signal, especially when we have any noise-related problem, being a digital plant, and it is going to be one of the issue. So when we have any frequency-based noise, whether it is going to be AC line or a high-frequency drive, and it is going to give some disturbance and to the infrastructure. And of course, the built-in oscilloscope feature, it also minimizes all these problems. And for example, if anybody do the installation like this, and the Fieldbus cable and the AC cable, if it is going to be mixed, and not only it violates the intrinsic safety principle, it also violates the Fieldbus installation principle. So such kind of things, and even if you do the expansion and anything happen, and the inbuilt oscilloscope will monitor the features, and of course it will tell exactly what is the problem. We can measure the frequency, and the frequency will tell us what exactly is the problem. So this is mixed with the 3-phase AC line. And there's also okay, so maybe in 2 minutes I'll finish this. So there's also a comparison study done between all the 3 different methods. So what is the value of this diagnostic? What is the value of the digital way of doing the instrumentation? So we take about 1,200 devices, and then we adopt this conventional method. We also adopt the Fieldbus method without any diagnostic. We just use the normal traditional components to troubleshoot. but we also have a field bus with fully integrated diagnostic. And the interesting factor here is, at the end of the day, the complete cost saving and the time saving and the field bus with the built-in diagnostic can be done for 1,200 loops in less than 3 days. Whereas in the normal conventional, it takes almost like 50 days. In the field bus, even if you don't build the diagnostic, that reduces the time into half. But of course,